So in this video we are going to talk about the word embedding. So in word embeddings we'll be talking about what is a word embedding, and we have already seen about the how to vectorize a particular document by using the bag of words. So in this video we'll be also covering a little bit more about continuous bag of words, CPOW, and apart from that we'll be seeing about the skip gram model, which is actually used in Word2Vec scenario. And yes, so we will also see a simple Word2Vec demo and also Word2Vec demo by using the skip gram model, and we'll be mainly using the concepts which are actually given by J. Alamar, because his way of explaining things is the best one which I could understand. So I will try to put it in a simple way and explain back to you with whatever is required. So if you want to know more about it, you can always research and understand it better. Okay, so let's get started. So I'll give a simple explanation about the Word2Vec model. So why we require it, how are we actually using it in our real life? Okay, say it's a simple example which is actually given here, a big trait X personality test. Okay, so say I am a person and I have various traits, character traits, right? So in that, if you could say I'm a good person or a bad person, I'm an introvert and I'm an extrovert. So here you could say that, say I'm taking the trait number 1, right? So trait number 1 could be like 0.4. So that is something like a dimension in your whole, whole data. And say if you are taking another trait, then you could consider that as your trait 2. Okay, so say introversion and extroversion. So in introversion I just get something around like minus minus 0.4, and extroversion, say I'm getting something around 0.8 or something like that. Okay, so but as time goes, or as say but with these two, probably you might not be able to identify how a person's character is, right? So probably you will have to add more number of traits. So we are not when we say it as a dimension, we cannot say that each of your dimension could be one particular trait. So as the dimensions or as the number of traits increases, the way it is actually represented will change. So it's all vague, or it is very difficult for us to understand in a Word2Vec, or because we are dealing with high dimensional vectors, but it is very difficult for us to identify or match it directly, okay, this dimension is this particular. No, we cannot identify like that. So there is some vagueness which will always come in the picture when it comes to the multidimensional data when we are actually working with. So say but just example, just identify that you got hit with say I'm a person, I got hit with a bus. So you want to find out similar people who can actually take up those job with the similar traits. Say I have got these two traits with these two particular values, and you are actually you have got two different people with these two particular values. So now what you have to do, how can you actually fill this particular my absence? You can fill this particular my absence with the most similar person, right? So the person with the most similarity in the characters could be actually replaced by for me, right? So that's where this cosine similarity comes in the picture. So you have two different data, and you are actually finding out a cosine similarity between like the first person and the second person, this first person and the third person, and say if you get a match of almost like 87% of match, then you will probably replace me with the person with a better match, right? So rather than this person, right? So this is how basically people work with the similarity measures. Okay, so so this is how the dimensions will look like. So dimensions are nothing but the various parameters which you will work with, but always understand there is a vagueness and you cannot just directly map it to the different ones, right? So always the major highlights of the word embeddings is that the main understanding which you have to keep in mind is that a person or a vector, or a person or a thing or anything could be actually converted or could be represented as a vector. Okay, so that is the main understanding which you have to keep in mind. So, and only when it is converted into vector, a machine can work with it, right? So anything which we work with could be converted into a vector. And the next one which you have to identify is that, and there is always a way that we could calculate the similarity between the vectors, so that we can easily identify how things. So these are the two major understanding which you have to have. So you can represent anything, even a person or a thing or whatever it is, document or whatever it is, as vector of numbers, and we can actually calculate the similarity between their numbers. Okay, so that we will understand which one is more. similar to each other. As we are talking about Word2Vec, I think, we should not miss this famous analogy. This famous analogy is that, say we have king, right? King is there and man is there. So just understand, like, each of these colors are nothing but your dimensions. So you don't worry about what each of those dimensions are. These are certain dimensions and there is a color code which is actually associated with it. So that's all. So if you could see, this is the king, traits, and this is the man traits, this is the women traits, and you are trying to find out with the queen trait. So and you are actually also trying to find out, like, man minus king minus man. King minus man means there are certain qualities that has to be there for a king, right? And you are actually taking out the man qualities from it and you are adding the woman qualities onto it. So who is that? That is nothing but a queen, right? Approximately it has to be a queen. So it's kind of an analogy, right? So when you do this, the amazing results have actually shown that the most amazing matches with the queen itself. Okay, so in the data you had almost like 400,000 word embeddings, and from within that the most closest match was actually with the queen itself, queen herself, right? So when you look at this, this is having some, with the colors it is very difficult for us to match, but still. Okay, so this has this analogy has actually, with the help of the word embeddings, have proved that all this kind of combinations basically work. So this is mainly used for the next word prediction. Say you would have seen like this in your mobile phones and in the internet and all. When you type something, you will get a lot of words coming as predictions, to fill in that particular gap, right? So this is one particular application where we use the word embeddings a lot. So in recommender systems, in next word prediction kind of applications, we can use this techniques. I mean, like, say thou shall, and then what could be the next word, so such kind of predictions basically uses this kind of language models which uses the word embeddings. So how we use them is like this one. Say you have the input features, say these are the inputs which are there, and you have some black box. Okay, so this black box is nothing but your language model, and it has to output, like, which word could be the best word as your final output, right? So this is how actually it works. Say in the black box, if you just open and see, it will be like, you will be looking over to the word embeddings, and then you will be calculating the prediction, then you will be projecting all the the most appropriate vocabulary which is associated with. Say these are all could be the words after thou shall, but after thou shall, say the prediction for this particular aardvark is just 0. So this R is actually 0, Aaron is actually 0.001, but this one has got 0.4. So if you have all the words, then you will take the best prediction value, right? So that will be actually considered as your next word after these two words, right? So this is how this prediction works. Hence you could use this word embeddings for next word prediction in the language modeling, right? So now here we're actually, we are talking about the continuous bag of words. So continuous bag of words, if you could see, these are the things which you have to understand. So this basically uses the embeddings, right? So for each word, we need to get the embeddings. And how can we get the embeddings to select the next word? By looking at the nearest words. I mean, like, say if you want to thou shall, then I mean, like, with these two particular words, we need to identify this one, right? And then again, these two particular words, you have to identify this one, these two different words. So it's kind of, n grams or 2 grams, like, you're taking two at a time, right? So there is a window. So the main thing which you have to identify here is that, you have a window of 3. So in the window of 3, if you could see, 2 are the input words, and for 1 could be your possible, prediction word, right? So 1, 2 and 3. Then again, you will take the next, I mean, like, the window is actually moved. The window will be actually moved to next to 3. So shall, not, then make. So these two are the inputs and make is the output. So when you look at here, say thou and shall are the input and not is basically the expected output. And when you look at shall, not, make is the expected output, right? So like that, you will change this window across your whole set of lines. So this is just a line, but just think about billions of documents or billions of data where you are actually working with. So you have to do it across all your data, right? So here we will actually pass through each one of them, and you will find out, like, you will change your window, like, then again you will change it to make, not make, then it should be a, then make a, then it should be machine, then actually machine in a machine in a machine, then it could be in, and it just goes on till you complete your whole things, right? So this is nothing but the continuous bag of words. In continuous bag of words, you will actually predict the output by looking over to the previous ones. I mean, like whichever is the previous one, you will actually take that, and then you will try to identify which one is the next one, right? Now comes the next model. Next model is basically the skipgram model. So skipgram model is actually the reverse of your continuous bag of words. So in continuous bag of words, you will take the nearest words and you will predict the next word. But in the skipgram model, you are trying to make it more accurate by you will consider the current word, and you will try to consider, I mean, like you will try to consider both the previous and the the words before that and after that. Okay, so you want to know this red. Okay, so this is what you want to get. So you will consider both the words which is before and after. Okay, so your input will be like, input will be by, a, and bus and in. Then you have to predict red. So red basically comes in between. So by a, red, bus, in. So this is how basically by a, red, bus, in. This is actually it is, but you will try to predict the other way around. So what you have to understand here is that your input is the current word. Okay, in skipgram model, your input is your current word. Your output can be any one of them. Okay, so it could be either by, or it could be either a, or it could be bus, or it could be in. It could be any one of them. So don't worry about the color codes here, but just understand, for the current word, any of this could be your relative words or the nearest words. So this is basically kind of an opposite version of continuous bag of words. So here when you see that, for the skipgram model, it's very important for you to consider the window size. This should be the predicted word, right? This has to be predicted, but this is our current word right now. So we are taking 2 words before, 2 words after. So totally, so this is the window that is actually, say when you change your window. So actually your window size is not 3 here, it's actually 5. Okay, so sorry for the confusion. So this is actually, here the window size is basically 5. So when you look at here, so thou shall not make a, right? So for this particular not, one word of not, okay, you will have 1, 2, 3, 4 outputs. Okay, so this is what you have to identify here. So, and then say here make, for that particular make, you will have all these outputs like shall, not, a, machine. So all these things are the outputs. So for a, then again you have all this output. So this is the one which you have to keep in mind in the skipgram model. So you're actually worried about the current word, and you are taking 2 words before, 2 words after as the outputs for it, right? And now actually doing is that we have this is called skipgram with the negative sample. So I will tell you why we go for this negative sample. So normally when you look at your example, you will have everything as target as 1. So that means that there is a higher chance for overfitting. That means once your model learns it, then there is a higher chance for overfitting. So what you have done is that you have actually, you're trying to include negative samples. So this negative samples are nothing but, leave all this. Negative samples are nothing but some sample words out from the dictionary which are not their neighbors. Okay, so shall, not, a, machine, these are all the neighbors, right? So apart from all these words, so for if any of the word comes here, then we will give this target as 1, but any other words, other than these 4 words comes, we will give it as 0. So how can we give it? We just randomly select 2 words from the vocabulary and we will give it as 0. That's all, because that anyway is not going to have an impact. But if you really have an impact, you can do that, but otherwise this this way of doing things will try to help our model to learn. And it's like it is making the model more accurate by giving hard challenges to the model to learn, because it's learning. Say when I'm trying to learn this particular model, it's actually doing it at a higher speed, right? So it has to be really accurate to get this done. So in this we actually talk about the Word2Vec training process. So in the Word2Vec training process itself, we pre-process the text and we have our size of the vocabulary. It's very important. And then while at the start of the process itself, we require 2 different matrices. One is the embedding matrix and the other one is context matrix. And this embedding matrix, for embedding matrix and context matrix, we should have our own vocabulary as well. So now at the start of the training, we have to initialize the matrices, right, with some random values, because we don't know whether it is the right value at the initial stages, right? And as each of the training step, moves on, then, we take one positive example and one its associated, negative examples. And then, we have to, make sure that it is done in a correct way. So what we basically does is that, say, we have 4 words. Just consider that we have 4 words. So, we have 4 words, so the input word is there, and we have the output word is there, right, and also the negative samples. So these are the here, it also shows you about this Aaron and Taco are basically the negative samples, right? So these are the negative samples here, right? So now what we does is that we look over to the embeddings here. Okay, so we look over to the embeddings for each input word, and we will try to, and we will also look in the context matrix. And then, so here when we when you look at it, you could see that there is an embedding matrix. So for the embedding here, we have this not, right? And for the not, you have its corresponding context. Context is like thou, Aaron, and Taco. So just consider this one, and its target we already know 1 0 0. So these are the negative samples, right? So what we basically does is that we will take the we will take the dot product. So this is basically the dot product of your input and output, and you will get some particular values, and whatever be the value which you get, you can actually convert it into a probabilistic function. I mean, like by, say, you can use sigmoid or linear functions, any of those, and convert it into a sigmoid function. So you will understand that for not and thou, you will get almost like 55% accuracy, and for not and Aaron, you are actually getting only 25% of accuracy. I mean, like percentage of similarity, and here not and Taco, you are getting almost 0.68 kind of similarity. So once we get the similarity, what do we have to understand? So we have to understand, now we have to learn our model. We have to make our models learn. And how can we do that? Actually, we will do that by finding out the error. Okay, so this is the entropy or error. Any entropy functions or error functions could be used here. So here we are just using 100 minus 0.55 or 1 minus 0.55. So you'll get this error rate. So you will understand that this is I mean, like according to the error values which you get here. So lesser error, you mean that means that you have more similarities. So you will actually take the errors, and you will actually do you will update the model with the new values. Okay, so you will update your whole model with the new values. So the embedding continues to be improved. So this doesn't mean that you are actually getting the right values. Your embeddings will get improved. So you could actually we can use this error to adjust the embeddings of not, thou, Aaron, and Taco, right? So all this this errors are basically taken, and we are updating the embeddings of all those, and the next time we can make this calculation, the result would be closer to the target values, right? So that means that we are taking these errors and updating these particular values, so that our whole cycle is actually improved. So now when we will stop the training process, we will stop the training process. So this context matrix is basically used for improving the results or improving the accuracy of your embeddings. I mean, like the embedding metric. So finally, once you are okay, you are good to stop this particular whole process of getting the results and updating your model, then finally you will discard this context matrix, and you will be simply taking this embedding metric. So these are called as a pre-trained embeddings. Okay, so say for Word2Vec and all, say you will get the pre-trained embedding models, so you can actually directly use that model for using in your applications. So now we will see about the demo for the Word2Vec. So this is a simple demonstration. So the first one basically talks about the NLTK package, and this is basically done using the GenSim model. And in the GenSim model, you do have this Word2Vec. So this Word2Vec uses the pre-trained embeddings so you don't have to load it separately, and it has got this function as such, right? And then you have this stop words, and you are also importing the regular expressions, and we are just taking a set of in a paragraph. So in this particular paragraph, if you could see, this is just about the Bahrain Vision 2030, and the first thing what we are doing is that we are just pre-processing the data by making it into a paragraph, and you are leaving that, and we are using this regular expressions for doing that. And then comes the so you are actually removing the 0 to 9, So here it actually talks about taking the digits and all those stuff, and then comes, and if you want to use this tokenize, you have to basically use this Pinkett. Okay, so here we are actually using the sentence tokenizer of the text, right? So here we are also, then we are actually taking, so we are converting it into sentences, then again into words, right? Then for I in the range, you are actually taking the length of the sentences. For the length of the sentences, you are actually moving from one word to another word, right? And you are also removing all the stop words in the English. So you will get the sentence of one as all these particular words, right? And then you are actually training the Word2Vec model. So Word2Vec model, you don't have to worry about the Word2Vec model because it's already there in the GenSim, right? It's generate similarity. So GenSim, so it is already there in the GenSim package library. So if you could see here, you are actually passing the Word2Vec and then the sentences. Okay, and the minimum count has to be 1, so at least one a sentence has to be there. And then finding the Word2Vec model. So model.wv, this is word vector. Okay, this is word vector of leaders. So I mean, like, which all words are actually closer to this leader. So that is what you're actually trying to find out. So you are getting a lot of an array with a lot of similarities. And then you say if you want to find out the most similar words which are related to the governmental, the term governmental itself. So if you simply print the similar, you will get that extensive, so addresses, so some are correct, some are not correct, that's all. So you will get all these terms as the most similar terms to this particular governmental. Then if you want to find out the most similar words to the vision, this means this makes more sense. I mean, like innovation, industries, governmental, so there are certain one more. So it also prints along with its the probability. So this is a simple algorithm where we could use the GenSim model to invoke the Word2Vec function which is already there in it. So you don't have to actually worry about the pre-trained embedding. So it actually invokes the pre-trained embeddings of Word2Vec. So whatever we see in the in there and whatever that final embeddings is there, so that embeddings are basically used to identify this, right? So this is the one method. And another method is basically by using the skip-gram model. So in skip-gram model, actually we saw about that detailed skip-gram model, right? So here we have to identify the corpus vocabulary, and then we have to build a skip-gram model. And for the skip-gram model, we should also have the target and the context, right? So that means, like, we will take the current word and we will also take the context words, right? And the relevancy. So here there is something called relevancy also. Then we have to generate the skip-gram model. Then we have to train the model to get the word embeddings, right? So this is what we are actually following here. So it's kind of more detailed way of just going through step-by-step process in the skip-gram model. So here first thing is that we have to build the corpus vocabulary. So for that we are just importing all the dependencies, and here we will be also using this TensorFlow and Keras. So understand, TensorFlow is actually kind of a platform, and which will help you to work with the machine learning models and the task, and Keras is kind of a library which provides you with all the algorithms and everything which is actually required to be used in the TensorFlow. Okay, so it's kind of like one thing over the other. It's kind of a stacked structure which we are basically going to follow. So here in order to install the TensorFlow, you can actually use this pip install TensorFlow. I think you would have already seen that in the in your machine learning machine learning course and artificial intelligence course. And then you are importing the TensorFlow. So you are actually importing it as TF TensorFlow, and this is the version. To find out the version, you can actually use this. And while you are using the TensorFlow, running the TensorFlow, make sure that your runtime has to be it has to be GPU. So that means that you have to go to the runtime and change the runtime to the GPU, right? So this is how you have to actually work. And then next thing which you have to understand is that you have to install the Keras. Okay, so whenever you work with the Google Colab, you have to make sure that you have this exclamation mark. So you have TensorFlow and you are importing the Keras, and then there are different type of models. Say in Keras the main. So when you look at the Keras documentation, you could see that there are different ways of you can actually generate the model. So this function API is one way of doing things. So it's a way to create the models, and another one is basically this one. This is actually the sequential way of doing things. So in the sequential class, you have this way of so this is also, say, tf.keras.sequential, right? So this is also sequential, means you will make sure you will tell the model like what should be the different layers that has to come before and after, and how you are actually making your model in a sequential way, right? So there are different ways of doing things like that. So this is what we are actually talking here. So here we are basically using a deep learning model. So we are using the sequential model here, and you have to import so many different functions like LSTM. The skip grams is the major one, but ma'am, can we just stick on to no, because as you are using the deep learning model, you have to use other imports also. So you have to just follow this as of now. And then comes this is our NLTK part. So from the NLTK part, because we are going to work something on the Gutenberg Gutenberg text, so text data, so textual data. So we have to basically get this Gutenberg, and we need Pimcat and stop words. So this is just for our, and our stop words are basically stored in the stop underscore words, right? Then for our operations, we are actually taking a Bible text. Okay, so we are taking the Bible, and here actually you could see that we are actually doing a stop word removal. So here, like, punctuation is removed and all the digits are basically removed from it. So when you look at the data, you could see that the King James Bibles, Old Testament, so like that, these are the words which you have in your Bible as of now. You have removed all this punctuation and all this 0 to 9, all these words and everything. Then in order to tokenize, so before tokenizing, you're actually normalizing the document. So kind of a pre-processing is basically done. So you are actually stripping it, and you are doing all this pre-processing, and you are getting all your data in the filter tokens. So when you get your normalized corpus, you will have np.vectorize of normalized document. So that means that you are actually converting all your data which you have here into vectors, and you are actually saving it in the normalized corpus, right? And then comes the unique word from the, you have to extract the unique word from the corpus and assigning it a numeric identifier. You are just going to identify the one. So for that, you are actually using the normal Bible, and you are actually taking one word at a time and checking whether they are unique or not. So if it is unique, you will add it onto the norm Bible. So like that, you will actually work here. Right, so this is just for extracting the unique words, and then you are using this tokenizer. So here actually using tokenizer function itself, and you are actually fit on text is like the function which is actually applied upon this norm Bible. So and in that, you are going through each word at a time, and you are identifying the vocabulary size. So vocabulary size is all the identifiers plus 1, right? So this is the vocabulary size that you are actually taking. Then you are actually going through each and every vocabulary thing, and going for each and every doc in the norm Bible, and for your printing the vocabulary size. So you have an vocabulary size of altogether 1, 2, and the unique words in your unique words are basically this one. So shall, one, unto, Lord, thou, thy. So all these are the words with its corresponding number of occurrences are also shown. Now we need to build a skipgram model. For the skipgram model, we have two things. We need two things. One is the target and the context, right? So this is how actually it will look like, and there is a relevancy generator. So relevancy. So here we are basically using the Keras function API provides a, so the function API is the model which actually in Keras which provides us model skipgram. So skipgram model. So we are basically using that. So as I already told you, there are two different models, right? So here we are actually using the function API. So here in order to generate the skipgram models, what we have done is that skipgrams of this is that word ID and the vocabulary size and the window size, and we are actually going through each word ID, right? And we are actually pairing pairs, and the labels is equal to skipgrams of each pair, and this is nothing but the labels, right? So we are actually forming a kind of a key value pair, like king how many times, and in the Bible how many times, and what is its corresponding so it is whether it is 1 or 0. 1 means what? 1 means it is nothing but it's a neighbor, and 0 means these are the negative samples. So like that we are actually generating it. Okay, so this is actually your input output and the input output and the target is actually, it could be either 0 or 1. So this is how you are actually building it, right? So this is the negative sample for the king, right? When you look at it, this is the negative sample for the king, and when you look at the Bible, you have this negative sample and this is a positive sample, like that you have actually given. For the James, you have negative sample and positive sample, right? So like that, actually you are actually developing all the negative and the positive samples for your whole data. So this is what you have done. So you should be able to relate it to what we have seen, okay, what we have seen. And then the next one is basically building the skip graph model architecture. So here we are not doing much, we are just following the steps and like sequential. So this is your complete skip graph model. I mean, like, this is the deep learning architecture that we use. We don't have to, we are not diving deep into this architecture as of now. We are just using the architecture which is actually provided as part of the system. And then the next step which we have to do is that about the training the model. So when we look at training the model, what we have to do is that the detailed steps about training the model. So when we train the model, we have to look over to the embedded matrix, and we have to also look at the context matrix, right? So these are the two different matrices which we have to look up. So here when we train the model, we are actually taking the epochs as 3 because it was taking a lot of time. So in order to complete it, so you can actually, if you have good specification and good system internet connection and everything, you can actually increase. It will take a lot of time, but you can actually increase. So here it will try to understand the loss and the number of the epochs and the loss at each cases. So here for the epoch 1 you have got a loss of this one, for the epoch 2 you have got a loss of this. So like that it is showing you. And then to get the word embeddings, what we have to do is that we have to extract the same from the embedding layer, right? So how can we do that? We can do that by extracting the weights of the embeddings from our word embedding model. So that means that you are using the scale-on package and you are using the Euclidean distances. So you have this word embed layer, and here you are actually giving the weight of it, right? And the distance matrix is basically Euclidean distance. So you are calculating based on the distance, right? And the similar words which you are actually giving is by using the distance matrix itself. And you are actually searching for the terms like God, Jesus, Egypt, and John, and the famine. So when you look at here, so God, it confirms like a certain set of words from the vocabulary, and here for the Jesus, it actually, what did you understand from all these things is like the model gives nearly correct words related to the target word. So God confirmed, disperse, strive. I mean, like, it's not very perfect, but it's okay, as accuracy can be increased by training more number of epochs. Say if you want to increase the number of the epochs, whatever is actually displayed here, these words which you get will also be more related to the more related terms to this particular thing. So this is an example of Word2Vec program. So in Word2Vec program, the main thing which you have to understand is that you are using the skip graph model. So in skip graph model, so it's not only, I mean, like, say you have your current word and you are actually having the target, I mean, like the nearby words also. The nearby words, you will actually take the before words and the after words, and then you will make them as its target as 1. And in order to make the system train in a better way, you are also giving extra negative samples by giving it as zeros. Okay, so in such a way that your model will be trained in a better way and try to start giving more I mean, like, more accurate results in the next run. So, and another thing which you have to keep in mind is that you have to decide upon the number of the epochs while training there. So as you increase the number of the epochs, definitely you will get better results, but as you keep on increasing the number of the epochs, what happens is that there is a higher chance for outfitting also. So you need to decide upon the number of the epochs based on your experimental process, right? So according to what you actually have and how you actually prepared and everything as well. So that's all about the Word2Vec. So we have seen a simple Word2Vec. So you should understand that for Word2Vec, you don't have to develop anything from the scratch. I mean, like, you should have a clear understanding about how you can actually do it with the existing algorithm. So from the scratch, you don't have to learn, but you have to take the particular data and use it in the way we want in our applications. That's all. So hope you understood. And even you can actually, once you build your once you build your Word2Vec model, you can actually even save those particular models for future uses. That is also possible, right? So thank you so much. If you have any doubts or anything like that, you can always get back to me. No problem. Thank you so much.